This is the second part of the chapter 26 homework preview, and in this part I'm going to go through numbers 46, 47 and 67. So let's get started. Here I try to draw for you number 46. So what it gives you, if you read the question, is it tells us that the voltage in some area is given by this equation. Right, so you got an x and a y-axis, kind of like a map, and it tells you the voltage as a function of x and y. And they're meant to be in values in meters. We are asked to find the electric field at a certain point, namely at the point 2.0, 2.0. So what does this actually look like? I try to draw the contour lines here, those lines of constant V, the equipotential lines. Now, if you've done a bunch of geometry, you may recognize this kind of shape, number times x squared minus other number times y squared, as giving you hyperbolas. Right? And that's what I've drawn here. So, first of all, voltage is 0, right, where this is equal to this. So if those were the same value, 150, 150, would be x equals y, or x equals minus y, because the sign doesn't matter once you squared. But because they're not quite the same, essentially the x needs to be a little bit bigger than the y, so that this thing is the same as this thing. So it gives you this kind of shape. These are the 0 lines. And then if you just, plot, if you try to find lines of constant V, they're gonna look like this. Now the easiest way to see this is you go to some kind of graphing software. You can use something like Wolfram Alpha online and just type in plot this function. And if we say just go along the axes, right? If you go along the x-axis where y equals 0 the whole time, well, as this gets bigger, the voltage gets bigger, so it's kind of going here towards the mountaintop. I mean, it keeps going higher, higher, higher. It never gets to the top, but it keeps going up. And the same thing is to the left. As you go to the left, you go up, up, up. In fact, you go up steeper, 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 higher, higher. Whereas if you go along the y-axis up or down, right, sign doesn't matter because it gets squared. So if the x value is 0, because you're staying on the y-axis, well, that means there's a negative sign here. Going to go down, 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 deeper and deeper down. Same thing if you go the other way. That gives you kind of this shape. Now you don't actually have to be able to visualize this in order to answer the questions, because what it's asking us to do is to find the electric field. The relation between the electric field and the potential is this one here. Now, we understand intuitively what this is, hopefully by now, right? It's essentially saying take the slope of this and then with the minus, in a downhill direction. Without the minus, it would be the slope in the uphill direction. That's what this vector grad v means. If you actually want to evaluate it, this is easy. You just take x, and this means as a vector, you take the derivative of v with respect to x, and for the y component of the electric field, you just take the derivative with respect to y. Now I made my d's curly, they're partial derivatives, but if you haven't met partial derivatives yet, it doesn't matter, because you do exactly what you think you should be doing here when you take a derivative. If you take a derivative of v with respect to x, you just do that according to the rules that you know. You just ignore the y. That's all there is to it. Right? Technically speaking, what this means is take the derivative of v with respect to x, keeping y constant. Like, treat y as if it's a constant. And this one, take the derivative of v with respect to y, pretending x is a constant. But chances are, if I gave you this and, I said, solve it, and you've never seen it, and you say, I've never seen it, I say, solve it anyway, you'd probably do the right thing. Right? Okay, let's do this. So Ex is minus dV dx. V is 150x squared minus 200y squared. Well, this thing is just a constant if you're going along the x direction. So I'm just going to get minus, I'm differentiating this with respect to x, 150, take down the 2, minus 300x, and ey, well, you figure it out. Right, same idea. And then, well, you want to evaluate this. Ex and ey at the point x equals 2.0 and y equals 2.0. Right, you work out general expression. Now, if I plug in for the x component of the electric field, I just plug in this. Okay, it's only x. The y has dropped out completely because there's no cross term that involves both x and y. So I just plug in 2. I get minus 600. You figure out the same thing for the y component, and then it's asking you to express it in terms of an angle and the magnitude, but you know how to do that by now. Right? You know how to go from components of a vector to angle and magnitude. The crucial thing here that was new, fairly new, is actually working out this explicitly. And we understand intuitively, okay, this grad of v is the vector that points down the hill in the sort of steepest direction, and the magnitude of that vector is the slope. Evaluating it, well, the minus sign is a minus sign, and then I just take the x component of this is going to be dv dx, the y component dv dy, and that's it. That's all there is to it. It looks mysterious, right? But it is not. It is really straightforward. It's just a kind of shorthand for writing out explicitly a vector with this component, the x, this component in the y, and if you put a z, then, well, there'll be another component there. Okay, I hope this makes sense. So this is 26.46. Let's go to the next one, 26.47. 26.47 is very similar to 26.46. It's just a different function. Again, we're given an explicit expression for the value of the potential. If I try to plot this, you can notice that as x and y go to 0, right at the origin, right, this becomes infinite, 200 over 0. So I can't really draw this. As I go closer and closer in, it's kind of this high, imagine this like mountaintop that it gets steeper and steeper and steeper and so reaches infinity. It's infinitely high right in the middle. Now, if you're paying attention, you probably notice that x squared plus y squared take the square root, right? If I have some point here, then x squared, y squared, the square root of this is just the distance, the radius from the origin. What this tells you is that this function is the same as long as you're the same distance from the origin. It's like 200 divided by radius. So the potential here falls off as 1 over radius, and you get circular equipotential lines. As long as it's the same distance from the center, same voltage. So perfect circles. Better than I can possibly draw them, of course. But again, even if you didn't see that, if you read it and it is not immediately clear to you what this function means, right, and it'll just come with practice, with working with more different types of functions and so on, but even if you can't see that right now, you can still work out the electric field, right? Just like before, the electric field is minus the grad of v, and again, it's not mysterious, it's in the x direction. If I write the electric field, like this, it's a vector ex, ey, maybe this of column form, well then I just put minus dv dx, that's the x component, minus dv dy is the y component. Okay, now I've got a function, let me write down again, my function is 200 divided by x squared plus y squared. Now, I'm going to take the derivative of this. It's not too bad. I'm just going to write it. Let me write it out now, not in the vector form, but work with the components individually, just to make my life a little bit easier. Minus dv dx is going to be minus the x derivative of this. So I can take out a 200 and a minus. minus 200 d dx of 1 over this. We're just taking the derivative. That is easy. I know how to do that. I'm going to apply the chain rule. It's minus 200 times minus 1/2. So this is x squared plus y squared to the minus 1/2. Let me write out just actually like this intermediate step. Because these kinds of functions, they show up a lot, so it's useful to just get good at differentiating them. X squared plus y squared to the minus 1/2. Right? Minus here. Minus 1/2 in the exponent. So I just apply my rules of differentiation, right? Square roots are no mystery. Just a minus 1/2 exponent. So I get minus 1/2 x squared plus y squared to the minus 3/2, right? Reduce the power by 1. Minus 1/2 goes to minus 3/2. But then, chain rule, right? I want to differentiate the thing inside. So I'm going to get the x derivative of the thing inside. It's just 2x. In case it's still not clear, let me write this out. This part here is d of d with respect to x squared plus y squared of x squared plus y squared to the minus 1/2. Right? Take the derivative with respect to this of this. You can think of it as ddr of r to the minus 1/2. Or dd, let's call it dd. Like, imagine this is just a z, right? And I take d dz of z to the minus 1/2. You know how to do that, right? That gives me this minus 1/2 z to the minus 3/2. But then I have to multiply this by d of this dx squared plus y squared dx. Right? Chain rule. And you can do this, right? You should be able to do this anyway. Probably had lots of practice in the calculus course, but maybe it's been a while. Right? So this is this part here. Okay, so you can evaluate this, you can simplify it a little bit, but that gives you your x component of the electric field. Notice your x component in this case still depends on the value of y. But in the previous question it didn't. In the previous question, the x component of the field only depended on the x position, but it was coincidence. It was because the function was special. It was very simple. In this case, the x component of the field depends on where you are both in x and in y. And that's going to be the more general case. You do the same thing for the y component, and it's going to look extremely similar. In fact, it's going to look exactly identical, except this is going to be a y. Because x squared and y squared kind of appear in the same role, right? You could swap them and it would look the same. So you're going to get the x and the y component of your electric field. You can plug in the values that you're given. In this case, it's x equals 2 and y equals 1. And then, having done this, you can again convert your vector in component form into a magnitude and a direction. And I hope that is something you're able to do. So make sure you can make sense of this. You can perform the derivative. We're going to see those derivatives again. Then hopefully the concepts make sense of what you're trying to do, right? We're trying to find electric field. So we're taking the negative grad of the potential. And what does that mean? It means I'm just going to take to get the x component, I'm going to take this with respect to the derivative of this with respect to x. To get the y component, I'm taking the derivative of this with respect to y. Make sure you understand this, and then the problem becomes just mechanical. You just have to take a derivative. Okay, let's move on to the next one. Here's number 26.67. The idea here is that we have a capacitor we hook it up to a battery, and the battery essentially provides a constant potential difference. So what's going to happen is you connect it to the battery, and after a little while, after a very short while in fact, the capacitor will be charged, and the potential difference across it is given by the potential difference that the battery creates, which in this case I think we're given 3 volts. Now, there's a certain amount of energy stored in this capacitor, right? Potential energy, because they're essentially positive and negative charges held, and those positive charges in the plate, they don't like each other. The negative charges in the plate, they don't like each other. So there's potential energy here. The amount of potential energy is given by this, the capacitance, times delta V squared. And why is this the expression? I suggest you read this. It's very short, just the part on page 729. But the idea is you imagine you sort of slowly build up the charge in the capacitor, and every time you want to add another electron, say, right, you have to overcome a larger number of electrons already on the plate. So if you're trying to like squeeze in more and more electrons in, every time it gets harder, so that every time you add one, the potential energy, the added potential energy is a bit bigger. And so what you're actually doing is you're doing an integration from adding a tiny amount of charge to an empty capacitor to adding a tiny amount of charge to an almost full capacitor step by step. This gives you this. Let's make sure you read the section. It's very easy actually. So please read through that to make sure you understand where this comes from. Okay, so now we're told we're going to use the charge stored here. Why would you want to store a charge, right? Well, one use of it is, for example, in a flashlight on your camera. You suddenly want to give out a bright light, you need a lot of energy. Your battery can't really provide that, this brightness suddenly. So you just build up a charge, kind of like a storage, and then you just, by closing a switch somewhere, you connect this up. Say here, if I put a light bulb over here, right, this is a symbol for a light bulb. I might have a switch here, like this. So now the switch is open. This is my switch. Nothing happens, but there's a wire here. But as soon as I close it, suddenly this extra charge is like, oh wow, I can go through here and neutralize the other side. So that the stored potential energy is dissipated by going to the light bulb, dissipated as a bright light until the capacitor is empty. That's kind of the idea here. So the total energy stored is this. We don't know C. That's in fact what we're trying to find. That's what we want at the end. Want this ultimately. But what we do know are 2 things. We know that the energy given off, well, it's done by this flashlight, and it's given by the power output times let's call it the duration of the light in this case, right? So the light is on for 10 microseconds or something. The power output is given certain wattage, right? So that a light power is energy per second. You know the number of seconds. So as long as you convert this to seconds, you're going to get the total energy given off. That energy comes from the capacitor. So those two are the same, of course. So that allows you to calculate the energy. Using the energy, you can calculate C. Okay, so that was 26.67. You fill in the details here and make sure you understand where this comes from. This was part 2 of the homework preview. In the last video, I'm going to preview problem 81, which is more challenging than all the previous ones. I'll see you there.